Good afternoon, sir. My name is Astha and I am from Dr. Kuntal Manna's research group. Here, I have analyzed three chemistry papers that all use metal organic frameworks or MOFs. The first paper from Inorganic Chemistry 2024 develops an iron catalyst for converting benzene to phenol. This is important because the current industrial process is inefficient. The second paper is from Anguvan Chemie 2025 that presents a nickel catalyst for methane activation. Nickel is significant because it's much cheaper than the precious metals typically used like rhodium, iridium, etc. The third paper is from Nature Communications 2018, that is not from our group, that describes a heavy metal trap that can remove 22 different metal ions from water with over 99% efficiency. These all three papers use metal organic frameworks which are porous crystalline materials and are used as platforms for their active sites. Now, for this assignment, my main objective was to use the Whiteside's writing of paper framework as a lens to analyze real research articles. More specifically, I first wanted to understand the principle of scientific paper structure described in the Whiteside's framework, that how a clear paper should be planned and organized. Secondly, I'm going to apply this framework to three chemistry papers and systematically check how their introductions, results, and discussions and conclusions are actually constructed. And then we'll identify where these papers follow the framework and where they deliberately deviate from it and what effect that has on clarity. We can also see here the analysis framework that contains understanding principle of scientific writing, apply Whiteside's writing framework, analyze structure of research papers, and identify effective writing strategies. Now we'll look on three papers one by one. Looking at paper one's introduction, we can clearly see that it follows a clear structure. It starts with the industrial importance of phenols and problems with current production methods. Then it reviews existing catalytic systems and their limitations. Next, it introduces MOFs as robust sports. It presents their key idea of using bipyridyl iron in UIO67 framework and ends with a clear goal statement. Now, this paper also deviates from Whiteside's framework, like it spends extra space explaining MOF chemistry before stating their research idea. The introduction is very long than the minimal template recommends. However, the impact of this paper is positive for readers unfamiliar with MOFs. This context is valuable. It's a strategic deviation that improves accessibility. Like by explaining MOF chemistry to a very extended version, it it helps the persons of non-MOF background to to understand the paper clearly. Now, after that, we will do the introduction analysis of paper 2. Paper two's introduction opens with a methane activation challenge. Methane's carbon-hydrogen bond is very strong and difficult to break. It reviews precious metal catalysts like iridium and rhodium that have very high cost. Then it proposes an earth-abundant nickel alternative in a MOF framework with the goal of selective monomerization. The deviations here includes a detailed mini review with specific performance numbers, and interestingly, they preview some results in the introduction itself that mentions performance data early. Here the impact is mixed. It's more detailed, but for experts it helps them understand the design logic immediately. So this is also a strategic choice. The paper 3 introduction start with water contamination and heavy metal toxicity. It reviews existing adsorbents like activated carbon and zeolites that pointing out they are ion specific, like each one only captures certain metals. They introduce their concept a broad spectrum heavy metal trap using EDTA grafted MOF 808. Their deviation include branding the concept early with detailed design features, including mechanistic reasoning about acid-base chemistry, and previewing dual applications that both adsorption and catalyst support. The impact of this paper is also positive because it makes the design criteria very explicit from the start, which helps readers understand the logic. One thing I really want to highlight about this introduction is how they justify their design. In many papers, authors just say we choose EDTA because it binds metals. It's a simple fact, but here they go a step further. They invoke hard soft acid base theory, which is also known as HSAB theory. They explicitly explain that EDTA has both hard and soft binding sides. This is a great writing move because it turns the paper into a rational design study, not just a lucky discovery. By explaining the chemical logic upfront, they convince the reader that the result had to happen. It makes the experiment feel necessary rather than random. If you're writing your own paper, this is a great tip. Always explain the theoretical reason for your material choice in the intro, not just the practical one. Now after introduction analysis, we'll go further to R&D section. Here I'm going to introduce the reverse engineering, the result and discussion section or R&D section. This means looking at the published results and discussion and working backwards to understand. We'll see some points like what experiments were done and in what order, how the narrative is built from synthesis to mechanism. And the last one is why the authors arranged it this way to make a convincing argument. It's essentially deconstructing the logic of the paper to learn how to structure our own R&D sections clearly. Okay, so let's look at the next slide. So when I started reading the results section of this paper, it could easily just look like a long list of data, but actually it's really cleverly built. It tells a story. Every experiment answers the next logical question. Let me walk you through it quickly. First, it starts with the basics. Did you make it? They show the synthesis and use X-rays to prove the crystal structure is solid. Simple but crucial. If the material is not what they say it is, the rest doesn't matter. Then they ask the deeper question, is it really a single site catalyst? This is the highlight for me. They use advanced spectroscopy to prove the iron atoms are actually isolated, just sitting there alone. That's important because if they were clumped together, the whole mechanism would be different. Then the big question, okay, does it actually work? Here they show the catalysis results 88% conversion with 99% selectivity. It's the money shot. And they don't just stop there, they show optimization data to prove the catalyst is stable under different conditions. But then comes the tricky part. Is it really the MOF doing the work or is it just iron leaking into the solution? They are smart about this. They run control experiments to show the iron is not leaching. They basically prove no, it really is our special MOF structure causing this reaction. Next is the why. How does the reaction happen? They use special tests to trap radicals and show that hydroxyl radicals are doing the job. Plus, they show you can reuse the catalyst, which is always a big plus. Finally, they wrap it up with theory. They use computer modeling to confirm the mechanism makes sense energetically. It's like closing the loop between what they saw in the lab and what theory predicts. So the whole flow is basically make it, prove it, test it, defend it, explain it, and then validate it. It's just a really clean, logical way to present research. No fluff, no random data, and just a solid argument. Alright, moving on to the paper 2. The story here is a bit different but follows the same smart logic. Since this paper is about methane, which is notoriously hard to activate because of the high bond dissociation enthalpy of CH bond, the authors have to be extra convincing. First, again, it start with the basics. Did they build the right catalyst? They synthesized the nickel catalyst inside the MOF pores and use spectroscopy to prove the nickel is really there. But more importantly, they prove it's in the exact right form, that is, a nickel dihydride species. That specific detail is the secret, so they spend time proving it right at the start. Then the big test, can it actually activate methane? This is where things get exciting. Methane is one of the toughest molecule in chemistry to crack. They show that their nickel catalysts work at 200 degrees Celsius to produce the borylated product. They report a 61% yield and a massive turnover number of 1388. To put that in perspective, that means one nickel atom is working over 1000 times. That's impressive efficiency. Now, the skepticism check. Is the MOF actually necessary? This is the cool part. They compare their MOF based nickel to a regular homogeneous nickel catalyst, which is basically nickel floating freely in solution. And guess what? The regular one fails completely, it just falls apart, but their MOF supported nickel is rock solid. This proves that the MOF is not just a container, it what saves the catalyst and makes it work. Next, they dig into the speed. How fast does it go? They do a kinetic study. They don't just say it's fast, they actually derive the rate law and figure out exactly how the speed depends on the concentration of reactants. It gives us a mathematical fingerprint of the reaction. And finally, the mechanism. What's actually happening step by step? They use computer models again to propose the mechanism. They show that the key step is something called the sigma bond metathesis. It sounds fancy, but it basically means the nickel swaps a bond with the methane in a single and smooth move. And their models confirm that this path is energetically possible. So the flow is really clean. Build it, prove it's active, prove the morph is the hero, measure the speed, and finally explain the mechanism. It's another great example of how to build a bulletproof argument step by step. Now let's look at slide 10, which is paper 3. It's a bit different because it's not about catalysis, it's about cleaning water. But if you look closely, the storytelling is exactly the same. It's all about building trust step by step. First, they start with the foundation. Did they make the material? They synthesize the special morph with EDTA grafted onto it. And unlike the other papers where they might use one or two techniques, they use three different ones: XPS, FTIR, and NMR. Why? Because they want to be super clear. Yes, the EDTA is definitely attached to the morph frame, it's not just floating around. They are leaving no room for doubt. Then comes the big reveal. Does it actually catch heavy metals? This is the headline result. They don't just test it on one or two metals, they test it on 22 different metals: lead, mercury, cadmium, and the result is almost always the same, over 99% removal. That's the moment in the paper where you go, wow, that works on everything. It's really satisfying to read. But then the critical question, is it really the EDTA doing the work? This is where they got clever. They compare their MOF EDTA with two other similar MOFs, one without the EDTA and one with a different chemical. The other two do a terrible job. The MOF EDTA is the only one that works perfectly. This proves that the EDTA is not just decoration, it's the actual trap. It's a very clean way to prove cause and effect. And then they take it further. Does it work in real life? Most people stop at testing single metals in a bottle of water, but these authors test a mixture of metals and run a breakthrough experiment. Basically, they pour dirty water through column and check what comes out the other side. It shows that the material does not just work in a textbook ideal scenario, it works in a messy, realistic one too. That's a huge credibility boost. And finally, the surprise ending. Can we use the trapped metal for something good? Usually, once you catch a heavy metal, you just dispose of it as a toxic waste. But here, they show that the trapped metal ions, like palladium, actually stay active. They use them to catalyze a chemical reaction, Suzuki coupling. It's like not only did we clean the water, but we also turned the waste into a useful tool. It adds a whole extra dimension to the paper. So the story is make the trap, show it works on everything, prove it's the right decision, test it in real conditions, and finally show a second life for the material. It's a really practical, application driven narrative, very clear and very convincing. Even when results and discussions are combined, they can be separated conceptually. Results are experimental measurements that what happened. Discussion is interpretation that why it happened and what it means. For paper 1, results include successful synthesis, 88% conversion with 99% phenol selectivity, and spectroscopy data. Discussion explains secondary coordination sphere effects, how hydrogen bonding controls selectivity, and why overoxidation is suppressed. For paper 2, the results include characterization data, 61% yield with 98% selectivity, and kinetic rate loss. Discussion explains stability of monomeric nickel, the mechanistic pathways, and comparison with other catalysts. For paper 3, results include characterization data and over 99% removal for 22 ions. Discussion covers EDTA interactions, multi-dentate chelations, enabling broad spectrum capture, and mechanistic comparison with literature. The pattern is clear. Results equal data and observation, discussion equals mechanistic explanation and significance. Now let's talk about literature comparison. Now you know how in the beginning of our writing we are taught that literature review is just about listing who did what, like author A did this, author B did that. Well, in these three papers, that's not what's happening. Here, literature comparison is used as a strategic tool. The authors are not just citing papers to look smart, they're using previous work as a benchmark to prove that their work is better. Let's look at how each paper pulls this off. Now, first one is benzene hydroxylation. The authors know that the field is full of iron catalysts. If they just said we made another iron catalyst, nobody would care. So what do they do? They directly benchmark their catalyst against two things: homogeneous iron salts. They show that when iron is floating freely in solution, it makes a mess. It produces a bunch of unwanted side products. Previous MOF catalysts, they compare their selectivity numbers directly. By doing this side by side comparison, they are not just saying we are better, they are showing a table where their number is 99% selectivity and everyone else is 70% or 80%. It instantly communicates value. It tells the reader previous attempts failed because they lacked this specific site isolation. We fixed that. It turns a simple result into a clear improvement. Now look at paper 2, which is methane borylation. This one has an even bigger challenge. Historically, activating methane has required precious metals like iridium, rhodium, or ruthenium. These are incredibly expensive and rare. So the literature comparison here is strategic. They don't just compare their results to other nickel catalysts, they compare their turnover number, that is 1388, directly against those expensive precious metal systems. And guess what? Their earth abundant nickel system actually competes with them. This is brilliant writing because it reframes the paper. It's no longer just about nickel, it's about sustainability. By comparing against the gold standard of expensive metals, they are saying you don't need a Ferrari engine to do this job anymore. Your economic car works just as well. That comparison gives the paper a massive impact. And finally, we have a Nature publication paper, which is paper 3. The benchmark here is different. They are not comparing against a single mechanism, they are comparing against entire classes of materials. They pit their MOF against the industry giants, activated carbons, zeolites, and ion exchange reagents. Here is the key move. They show that while activated carbon might be great at catching lead, it's terrible at catching mercury. Their MOF EDTA, it catches both equally well. They use a table or graph to show this broad spectrum advantage visually. This comparison is what justifies the whole paper. Without showing that existing material failed to catch multiple metals at once, their broad spectrum claim would mean nothing. The comparison is the argument. So, what's the big lesson for us here? It's that you should never just add a literature comparison as an afterthought or a mandatory related work section. Instead, use it to frame your advantage. Ask yourself what is the current standard, then how is my work clearly superior to that standard? and show the data side by side. When you write your papers, if you can make your literature comparison do this kind of heavy lifting where the comparison proves your novelty rather than just describing it, your papers will be infinitely more convincing. In this slide, we'll see the difference between abstract verse and conclusion. The most important distinction is between abstract and conclusion. They serve different purposes. For paper 1, the abstract reports catalyst development performance numbers, that is 1261 millimoles phenols per gram ion per hour with 99% selectivity and mechanism. The conclusion emphasizes why it works. Morph pore size prevents over oxidation and discusses design principles for future catalysts and significance for sustainable chemistry. And for paper 2, the abstract states the achievement 61% yield, turnover number 1388, 98% selectivity, and basic mechanism. The conclusion explains why active site isolation is crucial, identifies the turnover limiting step, and discusses broader impact for methane chemistry. Now, in paper 3, the abstract identifies the problem, reports the solution, and 99% removal for 22 different ions. The conclusion explains why this overcomes conventional adsorbent limitations, discusses practical water treatment to WHO standards, that is World Health Organization standards, and suggests future directions in green chemistry. The key insight is that abstracts are brief summaries of results for quick reading. Conclusions provide interpretation, significance, and future implications. Never just repeat your abstract in the conclusion. At last, here is the conclusion slide. All three papers broadly follow standard structure with strategic deviations that improve clarity. All the three papers broadly follow standard scientific writing structure. Introductions set up problems and solutions clearly. Like it follows similar format with minor deviations. Results and discussions build logical narratives from synthesis to mechanisms. Results are actually the data and the discussions are the interpretations, and both are distinguishable. And these are distinguished in all the three papers. Literature comparison, contextualized contribution. It like it can contextualize work within the field. And yeah, we talked about literature comparisons, and next one is the most importantly abstract summarize while conclusions interpret and inspire. There's a difference between abstracts and conclusions that are also seen in all the three papers. Understanding these structures help in reading papers efficiently and writing compelling manuscripts. It helps us to understand structure aids both reading and writing scientific papers. At last, thank you.